Our next speaker is Nikhesh Kumar Murali, who will be speaking about adapting CVXPY for optimization on curved spaces. He is speaking virtually, so hopefully he can show up on Zoom right now. And okay, while Stephen figures out what the situation is with that, I'll read his bio. He is a data scientist and interdisciplinary researcher working at the intersection of mathematics, optimization, and modern artificial intelligence. He holds an undergraduate degree in mathematics from the Indian Institute of Science, Bengaluru, and a joint master's degree in artificial intelligence and data science from IIT Madras and the University of Birmingham. His research interests span convex optimization, AI for mathematics, and geometry of latent spaces for mechanistic interpretability. He has worked on topics ranging from metric geometry and Fuschian groups, automated theorem proving using lean, to responsible AI and computer vision tasks such as object detection. He is particularly focused on how tools from differential and hyperbolic geometry, optimal transport, and convex analysis can be integrated into solving fundamental problems. He currently works as a data scientist in industry where he designs and deploys machine learning systems and agentic AI architecture for code automation. All right, we see your slides. Can you try saying something? Okay, let me see.
Hello. Hello.
Hello, thank you so much. The floor is
Thank
yours.
you. Thank you. Thank you, Pat. I'm actually really nervous. Thank you, Pat, for the wonderful introduction. And a little bit, as Pat said, I graduated from math and went on to explore. Actually, I started with bio and then I graduated from math and then I explored artificial intelligence and I'm currently working in the industry. So my talk for today is adapting CVXPy for convex optimization on manifolds. And before the beginning, I want to say that my motivation is purely mathematical, and mostly it kind of arose from my curiosity into delving deeper into Riemannian geometry, mostly theoretical aspects of optimization and math. So please excuse me if I don't have much of an software-oriented research here. But I just started, I was very curious and I just started playing around with CVXPY just a month or 2 months ago. And then I thought, okay, why not let me just do a little bit of research into it and try to come up with some kind of idea which can be contributing to the progress of this software. So, the main motivation is convex optimization. It's a workhorse for machine learning and artificial intelligence and whatever data we are receiving, and most of the engineering tasks, because it gives you the global optimality guarantees. One of the basic theorems in convex optimization is that any local minima or a maxima is also a global minima and a maxima for a convex function. So there you go. So convex optimization is really powerful and it's widespread used. CVXPY makes Euclidean convex modeling easy. As Boyd, Professor Boyd said in the earlier presentation about how easy it is to use a lot of variables and try to do optimization. But modern representations live on curved spaces and dynamic word hierarchies. Uh, we in NLP task we have embeddings on which most of the words and their representations and their relationship between different words are really complicated. So, and Euclidean space embeddings, although it makes sense, mostly it doesn't give much. way to use non-linear or very complicated relationship between words, between tokens, and between different entities. So what can we do? So that is one of the questions. And the goal is to adapt convex modeling to hyperbolic manifolds via g-convexity and h-convexity. This g-convexity, the geodesic convexity, was introduced long back, and the h-convexity, horospherical convexity. I read an interesting idea last year from a paper. So I thought, why not? Let me try to play with and try to use it to solve some convex optimization problems. The main idea is to do algebra or optimization in the tangent space of the manifold at a point and then map it back via exponential map. So this is the main idea. And the core of this is that the tangent space is locally Euclidean and the exponential map is locally, linear. So it makes it easier to do algebra or optimization, easier to store and evolve the gradients and pass the gradients. So let me move on. So this is the roadmap, geometry, then covering G-convexity, H-convexity, and then algorithms, Riemannian gradient methods and proximal steps, and then implementation and integration with CVXPY, and then dataset applications and scaling to massive graphs. So, and I also must point out that I used fair amount of LLMs, Claude and Gemini, to proofread the code because I made some kind of errors and debugging, and to format the frames of this talk and to streamline the organization of this talk. So basically, convexity in Euclidean space, a function is convex if we can try to um, find a point in between such that it also lies inside this region. So this is essentially the definition of a convex function. And we have when we have a smooth function, which is a differentiable function, then we have this first order inequality for convexity, which is equivalent, and Hessian. The Hessian is always non-negative. So why does it matter? Why we are interested in convex function is that any local minimum is global, and first order methods, especially with using Taylor series of approximations, are predictable. So for equivalently, for manifolds, we replace straight lines with the geodesics and the gradients or Hessians with the Riemannian metric Hessians. So manifolds for optimization, a smooth manifold is a space that locally looks Euclidean. So I don't want to delve more into math. I just want to say that it looks like locally like a Euclidean space, and at each point there is a tangent space, which is a vector space. Since a manifold can be curved, it can be distorted, it can be very convoluted, we cannot define a vector space on a manifold. But what we can do, what we can get the best out of it is we can define a tangent space, which is a vector space. So a Riemannian metric defines inner products on the vector space, and we have this length and the concept of length, the concept of distance. So geodesics generalize straight lines, so they are locally shortest paths on the manifold. My main idea was to do algebra in the vector space, the tangent space, and then map it back to the manifold using the exponential map. Um, the hyperbolic manifold is a negatively curved space, and we can model it using the Poincaré model, where the metric, the hyperbolic metric, defines it such a way that all the points are within 1 unit distance. So this is a ball, and then all the points within this ball are defined to be less than 1 unit distance from the center. So here the geodesics circular arcs are orthogonal to the boundary and diameters. Why do we care about hyperbolic manifolds compared to the Euclidean flat space? Is that we have stable numerical computation, we can do easy retraction mapping, and it can be used widely for embedding purposes. So it has a constant negative curvature. It has more room than the Euclidean space. So we can try to insert a lot of words in between. and try to find how much of a distortion they have if we kind of play around with it. If you kind of give an input king, queen, or a minister, rich, poor, you can see how it changes. Instead of linearly calculating the relationships, we can try to combine more nonlinear factors into representation of the relationship. And in this model, the points near the boundary are far away in the hyperbolic distance. So this means it has a very good inductive bias for word hierarchies. So distances can grow exponentially within the radius. So we can capture a lot of relationships between the word hierarchies. So some examples are tree embeddings, word net. We have graph embeddings within hierarchical structures, and then we have latent spaces for structure generative models. So what tools do we have for this Riemannian optimization? We have a manifold M with the tangent space, and then we have a Riemannian gradient at and the tangent space, and we have this update rule. So this update rule is basically what it says is that we do convex optimization on the tangent space, but map it back to the manifold using the exponential map. So these maps approximate to reduce the cost of doing this operation. We introduced the notion of geodesic convexity. So a function is g-convex for any points on the manifold and any geodesic locally shortest path, and we can have this convexity over the geodesic. If you go back to the definition of convexity here, it just this is a straight line is a geodesic in the Euclidean space. That's the reason we have this equation of a straight line here. Since we are dealing with manifolds, we just tweak the definition and make it that on the geodesic, it should be convex. So under suitable conditions, similar to the Euclidean convexity, we have that local minima are same as global minima and local maxima are same as global maxima. So this enables well-behaved first-order methods and proximal frameworks on this manifold. So we have different means to verify g-convexity. We can build objectives from known g-convex primitives, distance function or fresh means, and then we can check whether the Hessian of the function is non-negative when it's computable, and we can sample along random geodesics and verify that whether the function is convex and the geodesic. And I want to talk about the sectional curvature. So in flat spaces, the sectional curvature stays zero. So geodesics are parallel in the Euclidean sense. When the geodesics converge, so when the sectional curvature is positive, uh, it is similar to the sphere, and the geodesics converge. So the sum of angles in a triangle is greater than 180 degree. In the negative sectional curvature, the sum of angles is less than 180 degree, and the geodesics diverge exponentially. So it kind of distorts and gives more room between 2 points. So we call such spaces with negative sectional curvature as Hadamard spaces, which are ideal for global g-convexity analysis. In the case of negative sectional curvatures, the distance squared function is more convex than in the Euclidean space. So this means that we can accelerate convergence near the optimal values, and this will be very useful when we try to find optimal values for convex optimization problems. So Hadamard manifold is a complete, simply connected Riemannian manifold with non-positive sectional curvature. So the geodesics, why we are dealing with these negatively curved spaces is that any 2 points are joined by exactly one shortest path, which have no cut locus. And the another big advantage is that the distance function is strictly g-convex everywhere. So this means that we can do a lot of differentiation, lot of play around with it, and we have a very good flow of gradients. From G to H convexity, we need to refine this notion of G convexity so that we want the convexity to be defined as curvature independent of the manifold. So H convexity prevents the slowing down effects, which is usually seen as the points approach the manifold boundary. So when you have a negatively curved space, the points in the boundary are very problematic because then um, the slowing down effect takes place and it's very difficult to find the optimal values near the boundary. So we have some examples of Hadamard manifolds, hyperbolic space Hn, n-dimensional hyperbolic space, negative curvature -1, and then the flat baseline Euclidean space, and we have this symmetric positive definite matrices under the affine invariant metric. Those are used widely in imaging techniques. But I am interested in these hyperbolic embeddings, so I'll be going on about that. Some examples of g-convex functions are the square distance function, which is globally g-convex on Hadamard manifolds, and Frechet mean objective. So the minimizer is the Riemannian center of mass on the manifold for this function. And then on the SPD manifold of matrices, we have this negative of log of determinant, which is g-convex, which is used in maximum likelihood estimates, and then max of the distance to know the maximum distance of the ball enclosing a point or a space. So H convexity is a refinement to G convexity in hyperbolic space that accounts for the exponential expansion of the matrices. So if K is a subset of a hyperbolic space and is a G-convex set, then f of x equal to distance between x comma k satisfies the X convexity properties. So this H convexity allows for convergent traits that do not degrade as the optimization approaches the boundary of the Poincaré ball. So because because we are modeled in such a way that when the points are at the boundary, it becomes difficult to do convex optimization there. So we have refined this G convexity notion to H convexity. So it becomes easier for us to do optimization there. I just quickly compare gradient descent and stochastic gradient descent. So the gradient descent is the obviously the widespread algorithm which computes the exact gradient over the entire data set at every step. And then stochastic gradient uses a single sample and it's much faster per update and has low memory cost, better than gradient descent. It helps to escape local minima due to the stochasticity present while sampling the function. So I won't move on to Riemannian GD. So this is the same as the gradient descent, except that we are doing the exponential map to go back to the manifold. From we do the operation on the tangent space and then go back to the manifold to update these values. Riemannian SGD uses the unbiased stochastic gradient, and this is also similar to the SGD method we observe on the Euclidean space. So we need to consider some practical necessities like projection, retraction to enforce constraints on the hyperbolic space, learning rate, step size schedules, and numerical stabilization to avoid dividing by zero. So perform updates in the tangent space and then map back using exponential map. So what I did is experimental setup. In dataset 1, I did the synthetic tree structures to generate some 20 nodes and then recover the hierarchical structure in a 2D Poincaré disk. In dataset 2, I did word-node semantic relationships. I extracted the subsets of word hierarchies by giving some a set of 50 words and then map the discrete semantic distances to continuous hyperbolic coordinates. So the metric I used here is to measure how well the hyperbolic distances preserve the graph-based shortest path distances. some of the words I have given, and you can see how close or how similar they are on the hyperbolic space.
Nikesh, I'm so sorry to cut you off, but
Yeah. So I just
we're
quickly
a
I
little.
just quickly move on. Yeah. So what I did was that I just basically did the algebra on the tangent space and then mapped back to the manifold space using the proximal operators for your tangent spaces. And I just want to quickly say that I work mainly on the small data set, and exponential map is locally linear, so gradient descent blows up when the step size is too large, which means we get non-optimal results. I quickly go to the main algorithm. So this is my main algorithm in CVXPY manifold layer, and then first I take a point and then pick it to the standard Euclidean gradient map to Riemannian gradient, and then solve this constraint subproblem in the tangent space using CVXPY, and then find the optimal value, then retraction back to manifold using exponential map, and then for numerical stability, I perform some projection and then go back to the optimal point on the manifold.
Thank
So
you so
convergence
much.
of algorithms, yeah. So
Sorry.
this was the discussion I observed, and then this CVXY PY layer, this method I got 0.44, which is significantly lesser than the high curvature hyperbolic embedding, but significantly bit larger than the Riemannian GD results. So yeah, uh, I hope I conveyed my main idea of doing algebra in the tangent space and then mapping it back and using the CVXPY manifold layer to kind of do convex optimization and then integrate it with the CVXPY framework.
Thank you
Some
so much.
of the
Thank you.
future directions. Yeah, thank you.